For centuries, humans have looked at the night sky and asked one question: is there another world out there, close enough to matter? In 2025, James Webb may have finally answered that. A planet the size of Saturn, orbiting a star almost identical to our own Sun. Just over 4 light-years away, a world we might actually reach someday. Scientists who spent their entire careers searching for exactly this were stunned. Then something happened that no one predicted. It disappeared. The most powerful telescope ever built looked back at the same sky and found absolutely nothing. No debris, no dust, no farewell signal, like it was never there. Now the world's brightest minds are locked in a debate they cannot resolve. Some say it existed, others say it never did, and a few are quietly considering a third possibility, far stranger than either. This is not just a story about a discovery. This is a story about a mystery that is still unsolved, and the answer may be closer than you ever imagined. Before we dive in, if you love exploring these kinds of deep space videos, a simple like or subscribe really helps this channel reach more curious minds like yours. Now, let everything soften, and together we drift into space. 4.3 light-years. That is the distance between us and Alpha Centauri, the nearest star system to our own. In cosmic terms, this is nothing. A neighbour? The house next door. If the Milky Way were a continent, Alpha Centauri would be standing in our front yard. But 4.3 light-years is still 25 trillion miles. Picture this: if you could somehow travel at the speed of a commercial jet, cruising at 550 miles per hour, the way you might cross an ocean or a continent, you would still be flying for 5 million years before you arrived. That is longer than all human species have existed, longer than we have walked upright. You would begin your journey before the first stone tools, before fire, before language itself. And when you finally touch down at Alpha Centauri, everyone you had ever known would be dust. Their civilizations would be dust. The very shape of the continents would have changed. Even light, which crosses from New York to London in less than 2/100ths of a second, takes 4 years and 4 months to bridge that gap. And yet, in the grand architecture of the galaxy, Alpha Centauri A is practically next door. Among the 400 billion stars scattered across the Milky Way, this one burns just over 25 trillion miles away, 40 trillion kilometers. Out of an entire galaxy, we could not ask for a closer twin to our own Sun. Same spectral type, same surface temperature hovering near 5,800 degrees Celsius or 10,400 degrees Fahrenheit. Same steady nuclear furnace fusing hydrogen into helium in its core. Same golden light. If you want to find a world like Earth, a planet with liquid water, stable seasons, a chance at life, you start by finding a star like the Sun. Alpha Centauri A is that star. This is why, for decades, astronomers have turned their instruments toward this system with a focused, almost desperate intensity. They are not merely curious. They are haunted by a single tantalizing possibility: that the nearest star system to Earth might be hiding a world we could one day reach. Not in fantasy, not in imagination, but in the real, grinding logistics of human engineering and time. Because if a planet exists around Alpha Centauri A, if it sits in the habitable zone where water stays liquid and atmospheres can hold steady, it changes everything. It means the first world humanity might visit beyond our solar system is not buried thousands of light years away in some untouchable corner of the galaxy. It means the nearest possibility for life is within the narrowest conceivable reach. 4.3 light-years, a distance that remains monstrous by human standards, but just barely kisses the edge of what future generations might attempt. Picture this: the first interstellar probe, decades from now, maybe a century, accelerating toward Alpha Centauri. Not carrying humans, Not yet, but carrying cameras, sensors, instruments designed to taste the air of another world, to see if we are alone. That dream begins here. We have been looking at Alpha Centauri for as long as we have been looking at the sky. To the unaided eye, it appears as a single point of brilliant light in the southern constellation Centaurus, the third brightest star visible from Earth, outshone only by Sirius and Canopus. Ancient navigators used it, astronomers catalogued it. For centuries it was simply there, constant, familiar, unremarkable except for its brightness. But Alpha Centauri is not one star, it is three. The brightest component, Alpha Centauri A, is a yellow dwarf star nearly identical to our Sun. It is 10% more massive than the Sun, 22% larger in radius, and burns about 50% brighter. Its surface temperature hovers near 5,800 Kelvin. Its chemical composition mirrors ours. If you stood on a planet orbiting Alpha Centauri A and looked up at its sky, you would see a sun that looked almost exactly like the one we know. The second star, Alpha Centauri B, is slightly smaller and cooler, an orange K-type dwarf with 90% of the Sun's mass and 45% of its luminosity. Still a main sequence star, still stable, still long-lived. These two stars orbit each other in a slow elliptical dance that takes 79.9 years to complete. Their separation varies wildly across that orbit, from 11 astronomical units at their closest approach, roughly the distance between our Sun and Saturn, to 35 astronomical units at their farthest, about the distance to Pluto. They swing close, they drift apart, they return, a cosmic waltz that has been unfolding for 5 billion years. And then there is the third member of the system, Proxima Centauri, a dim red dwarf, barely 12% the mass of the Sun, flickering weakly in the infrared. It sits 13,000 astronomical units away from the central pair, orbiting them both in a vast, slow arc that takes roughly 550,000 years to complete. It is so faint that you would need a telescope to see it at all, but it holds a distinction that matters. At 4.25 light-years from Earth, Proxima Centauri is the single closest star to our Sun. This is our nearest stellar neighbour. Not one star, but a system, a small family of suns bound by gravity, evolving together, aging together. And because it is so close, we have been asking one question for decades. Does it have planets? The answer should be simple. Alpha Centauri is right there. We can see it clearly. We can measure its motion across the sky, track its spectrum, analyze its light in exquisite detail. If planets exist around those stars, we should be able to find them, except we keep finding things that disappear. In 2012, astronomers announced the discovery of an Earth-mass planet orbiting Alpha Centauri B. They called it Alpha Centauri BB. The detection came from radial velocity measurements, watching the star wobble slightly as an unseen planet's gravity tugged on it. The wobble was tiny, precise. The data seemed solid. The discovery made headlines. A potentially habitable world, practically next door. The scientific community was cautious but hopeful. 3 years later, the planet vanished. Reanalysis of the data revealed that the signal was not a planet at all, but an artifact, a ghost in the noise, produced by the way the radial velocity measurements had been processed. The wobble was real, but it was not caused by a world. It was a mathematical shadow. Alpha Centauri BB did not exist. It never had. This was not the first time a planet had been claimed and then retracted. It would not be the last. In 2019, a team using the Very Large Telescope in Chile detected another candidate, a faint thermal signature in the habitable zone of Alpha Centauri A. They called it Candidate 1, or C1. The observations were taken with an advanced infrared instrument designed to block out the overwhelming glare of the star itself, allowing fainter objects nearby to be seen. Over 100 hours of imaging, a point of light appeared at roughly 1.1 astronomical units from the star, about the same distance as Earth from the Sun. The brightness suggested something Neptune-sized. The position suggested it was moving, consistent with orbital motion. The team published their findings in Nature Communications. They were careful. They emphasized uncertainty. They noted that the signal could be zodiacal dust, or an instrumental artifact, or a background star that happened to align with Alpha Centauri by chance. But the signal was there, repeatable, persistent across multiple independent subsets of the data. It looked like a planet. Then, in August 2024, the James Webb Space Telescope pointed its mid-infrared instrument at Alpha Centauri A. Webb's coronagraph blocked out the star's light. The team scanned the region around it, searching for faint companions, and they found something, a point-like source at a projected separation of 2 astronomical units. Brighter than expected, warmer than expected, roughly Saturn mass, if the brightness translated correctly to size. They called it S1. The detection was clean. The object was confirmed to not be a background star. It was not a dust cloud. It did not match known instrumental artifacts. If it was a planet, it would be the nearest gas giant ever directly imaged around a sun-like star. The coldest, the oldest, a world that should not exist in a binary system this tight, and yet, there it was, or so it seemed. In February and April of 2025, Webb observed Alpha Centauri A again. 2 more chances to confirm the detection, 2 more opportunities to lock down the orbit, refine the mass, prove the planet was real. Both times the object was gone, not faint, not dimmer. Gone. How do you lose a planet? This is not a star that blinks in and out of existence. This is not a transient event, a supernova, a flare, a collision. This is supposed to be a stable, massive world orbiting a stable, ancient star. Planets do not vanish. They do not flicker. They follow predictable paths governed by gravity, moving in ellipses that can be calculated centuries in advance. And yet, at Alpha Centauri, we keep seeing things that refuse to stay seen. Some astronomers now believe that S1 and C1 might be the same object, 2 glimpses of a single planet caught at different points in an eccentric tilted orbit. If the planet's path is highly elongated, it would spend most of its time far from the star, visible to our instruments. But at certain points in its orbit, it would swing close to Alpha Centauri A, plunging into the overwhelming glare of starlight, where even Webb's coronagraph cannot see it. The planet would still be there, just hidden, temporarily invisible. Simulations suggest this is possible. In fact, when the team modelled thousands of potential orbits that fit both the 2019 and 2024 detections, they found that roughly half of those orbits would place the planet too close to the star during the February and April 2025 observations. Half the time, you would expect not to see it. A non-detection, in other words, does not mean the planet is not real, but it does mean we do not know yet. This is the pattern that has defined Alpha Centauri for over a decade. We see a signal, we analyze it, we announce it cautiously, we follow up, and then nothing, or something different, or something that raises more questions than it answers. The dream has always been simple. Find a planet next door, a world orbiting the nearest sun-like star, a place we could study in detail, a system so close that future missions, robotic probes, space telescopes, even interstellar craft centuries from now, could reach it within a human timescale. But Alpha Centauri is teaching us something uncomfortable. Proximity does not mean clarity. Being close does not make things easy. You would think that a star system just 4.3 light-years away would be simple to understand, that we would know everything about it by now, its planets, its dynamics, its history, that the nearest suns would be the best studied suns. Instead, Alpha Centauri remains a mystery wrapped in glare. The problem is not distance, the problem is brightness. Alpha Centauri A shines with a light of 1,000 Jupiters. Any planet orbiting it, even a giant planet, is a faint speck drowning in that flood of light. Blocking out the star without losing the planet requires instruments operating at the very edge of what is physically possible. Coronagraphs, adaptive optics, mid-infrared imaging. Even with the most powerful telescope humanity has ever built, we are still searching for shadows in searchlights. But Webb is not like other telescopes. It was not built to take pretty pictures of galaxies. It was built to see heat, to detect the faint infrared glow of objects too cold and too faint for any other instrument to resolve. It was built, in part, to find planets like the one that may, or may not, be orbiting Alpha Centauri A. If any telescope can confirm whether this world is real, it is Webb. And that is where the story truly begins. 1 million miles from Earth, the telescope floats in absolute darkness, not orbiting our planet, not tethered to anything, just drifting alone in the void at a place called Lagrange Point 2, a gravitational parking spot where the pull of the Sun and Earth balance perfectly, allowing the James Webb Space Telescope to remain stationary relative to both. It is one of the coldest operational scientific instruments humanity has ever built. Colder than the surface of Pluto, colder than liquid nitrogen. At its most extreme, its detectors reach 7 Kelvin, nearly negative 450 degrees Fahrenheit. At this temperature, steel would shatter like glass. Water would be harder than granite. Webb has to be this cold, because what it sees is heat. Every telescope before Webb looked at the universe the way your eyes do, invisible light. The rainbow spectrum, the colours we can see. But visible light is only a thin sliver of what exists. Beyond red, past the longest wavelength our eyes can detect, stretches a vast realm of infrared radiation, heat signatures, thermal glow, light too faint and too cool for human perception. This is where planets live. A gas giant like Jupiter does not shine in visible light the way its star does. It reflects some starlight, yes, but at close separations that reflection is drowned in the star's overwhelming glare. What the planet does emit constantly is infrared radiation, the leftover heat from its formation still radiating outward billions of years later. Not bright, not hot, just a faint thermal whisper against the cold of space. Webb was built to hear that whisper. Its primary mirror, 6.5 meters across, made of 18 hexagonal segments coated in gold, gathers infrared light with a sensitivity no previous telescope could match. Gold reflects infrared wavelengths better than any other material. Each segment was polished to a precision of 20 nanometers. Picture this: if you scaled one of those mirror segments up to the size of the United States, the largest imperfection on its surface would be less than 2 inches tall. This level of precision exists for one reason: to see things that should be invisible. But precision alone is not enough. Alpha Centauri A shines with the light of roughly 1,500 Jupiters. If a Saturn-mass planet orbits at 2 astronomical units, twice the Earth-Sun distance, that planet would be roughly 10 million times fainter than its star. 10 million to 1. Imagine trying to see a firefly hovering 1 foot away from a searchlight. Now imagine that searchlight is 1,000 miles away, and you are trying to see the firefly. This is the contrast ratio Webb must achieve. The technology that makes this possible is called a coronagraph. The concept is simple, the execution is not. A coronagraph places a physical mask, an opaque disk, directly in the focal plane of the telescope, positioned precisely where the star's light focuses. The mask blocks the star. The light from everything around the star, planets, dust, debris, passes through. It is an artificial eclipse, engineered with sub-pixel accuracy. Webb carries two coronagraphic instruments. The near-infrared camera, NIRCam, observes from 0.6 to 5 microns. The mid-infrared instrument, MIRI, covers 5 to 29 microns. Both use occulting masks that sit at the first focal plane, blocking the star's core while allowing the surrounding field to be imaged. MIRI's coronagraph uses a 4-quadrant phase mask design, which introduces a 180-degree phase shift in the transmitted light, causing it to interfere destructively when re-imaged. The result, starlight cancels itself out. The planet remains, in theory. But Alpha Centauri does not cooperate with theory, because Alpha Centauri is not one star. You can block Alpha Centauri A. You can place the coronagraph mask directly over it, dimming its glare by a factor of 10,000 or more. But Alpha Centauri B, the companion star, the second sun in the binary, remains unmasked. Its light floods the detector. It saturates pixels. It creates diffraction spikes and scattered light across the entire field of view. You're not just trying to see a firefly next to one searchlight. You're trying to see it between two searchlights, and you can only block one of them. This is what makes Alpha Centauri uniquely difficult. Not distance, not faintness, complexity. The system is a gravitational tangle. Two sun-like stars locked in an 80-year dance, their light blending, their orbits crossing, their combined glare overwhelming any faint companion that might exist between them. Ground-based telescopes have tried. Space telescopes have tried. The Hubble Space Telescope observed Alpha Centauri repeatedly. Every attempt faced the same wall. The binary drowns the signal. The team at the Space Telescope Science Institute knew this. They knew that pointing Webb at Alpha Centauri would require something no previous observation had needed. A custom observing sequence designed specifically for this target. Webb was not built to look at nearby bright stars. It was built to peer 13 billion light-years into the past, to see the first galaxies forming in the infant universe. Its instruments were optimized for faint, distant objects. Its detectors were tuned for long exposures. Its pointing systems were designed for targets that barely move across the sky. Alpha Centauri moves. It is so close that its proper motion, its apparent drift across the celestial sphere, is easily measurable over weeks. For Webb to track it precisely, the telescope's fine guidance sensors had to lock onto reference stars and compensate for that motion in real time. The exposure times had to be calibrated carefully to avoid saturation. The coronagraph alignment had to be perfect. If the mask drifts even a fraction of a pixel off-center, starlight leaks through and the observation fails. Charles Bateman from NASA's Jet Propulsion Laboratory and the NASA Exoplanet Science Institute described the challenge this way. These are incredibly demanding observations to make even with the world's most powerful space telescope, because these stars are so bright, close, and move across the sky quickly. And yet, in August 2024, Webb succeeded. It pointed MIRI at Alpha Centauri A. The coronagraph engaged. The 5-layer sun shield, the size of a tennis court, kept the telescope cold. The detectors activated, and for hours Webb stared into the glare, blocking the star, searching for heat. It found something, a point-like source. Faint, steady, located at a projected separation of roughly 2 astronomical units from Alpha Centauri A. The signal was confirmed to not be a background galaxy. It was not a foreground asteroid. It was not an instrumental artifact. The brightness suggested a planet, roughly Saturn mass, with a temperature around 225 Kelvin, cold enough to have a thick atmosphere, old enough to have cooled from its formation heat, close enough to be the nearest directly imaged gas giant around a sun-like star ever detected, if it was real. But here is what Webb cannot tell us yet: whether the planet is actually there. One detection is not enough. Planets move, stars move, dust drifts, instrumental noise fluctuates. To confirm a planet, you need to see it again. You need to measure its motion. You need to rule out every alternative explanation, Not just plausible ones, but implausible ones too. You need to observe it from multiple angles, at multiple wavelengths, over multiple epochs. Webb tried. In February and April 2025, it observed Alpha Centauri A again. Same telescope, same instrument, same coronagraph, same target. The object was gone. This does not mean it was never there. Orbital simulations suggest that roughly half of all possible stable orbits would place the planet too close to the star during those observation windows, hidden in the glare, temporarily invisible, waiting to emerge again months or years later when its eccentric path swings it back into detectable space. But it does mean uncertainty remains, and uncertainty is the cost of pushing a telescope beyond what it was designed to do. Webb was not purpose-built for Alpha Centauri. It does not have the wavefront control systems needed to independently suppress two stars. It does not have the adaptive optics to compensate for binary dynamics. It is doing the best it can with instruments built for a different kind of sky. And yet, that best is better than anything that came before. If Webb confirms this planet, if future observations recover the signal, refine the orbit, measure the spectrum, Alpha Centauri will transform from a postcard into a laboratory. We will be able to study a giant planet around our nearest stellar. Neighbour in detail no other exoplanet has ever received. We will see its atmosphere, measure its temperature, map its clouds, understand how planets form and survive in binary systems. But first, we have to find it again, and that search has only just begun. August 2024. Webb's detectors were already active when the data started streaming back to Earth. The observation had been running for hours. The coronagraph was locked on Alpha Centauri A. While the 5-layer sunshield held the telescope at 50 Kelvin, the mid-infrared instrument, MIRI, was cooled even further to 7 Kelvin, staring at the region around the star, capturing the field in deep exposures, searching for heat where no heat should be visible. Charles Beichmann sat at his workstation at NASA's Jet Propulsion Laboratory, waiting. He had been waiting for this moment since 2017, 7 years earlier, when Webb was still being assembled on the ground, and the idea of pointing it at Alpha Centauri seemed absurd. He had sent an email to colleagues back then, proposing the observation. The opening line was half joke, half challenge. When you stop laughing, let's think about doing this project. Some of them did laugh. Webb was not. Designed to look at bright, nearby, fast-moving stars. It was designed to see the first galaxies, objects 13 billion light-years away, so faint they had never been glimpsed by any telescope. Alpha Centauri was the opposite. Brilliant, close, moving across the sky at a speed that would blur long exposures, and sitting in the middle of the galactic plane, surrounded by thousands of background stars that could contaminate the data. But Beichmann believed it was possible, and now, in August 2024, the data was coming in. The search was not random. If a giant planet existed around Alpha Centauri A, it would have to orbit within a narrow band, close enough to the star to be gravitationally stable despite the presence of Alpha Centauri B, but far enough out to remain detectable above the coronagraph's inner working angle. Computer simulations suggested this band extended from roughly 1 to 3 astronomical units. Closer than that, and the planet would be lost, in residual starlight. Farther out, and the gravitational influence of the companion star would destabilize its orbit over millions of years, flinging it into interstellar space or sending it crashing into one of the suns. That narrow band, that sweet spot between invisibility and chaos, was where Webb needed to look, and it had to see heat, not reflected light. A gas giant the size of Saturn reflects only a tiny fraction of its star's light, not enough to stand out against Alpha Centauri A's glare, but even a cold gas giant radiates infrared energy, leftover heat from formation, thermal emission from atmospheric compression, a faint glow at wavelengths between 5 and 29 microns, precisely the range MIRI was built to detect. The contrast ratio was staggering, roughly 10,000 to 1. Picture this. If Alpha Centauri A were a 100-watt light bulb hanging in your living room, the planet would be a birthday candle flame held 1 foot away from it. Now imagine trying to see that candle flame from across town. That is what Webb was attempting. The first pass through the data revealed nothing. Raw images from MIRI are not clean. They are flooded with instrumental noise, cosmic rays, detector artifacts, scattered light from both stars in the binary, and contamination from the thousands of faint background sources scattered across that region of sky. Before you can see a planet, you have to remove everything that is not a planet. You subtract reference images. You apply point spread function corrections. You mask bad pixels. You filter out known sources. The team worked methodically. Aniket Sanghi, a PhD student at Caltech and co-lead author on the project, led the data processing. He had chosen Alpha Centauri deliberately, he would later say, because it was one of the most challenging objects he could find. Direct imaging is always difficult, but direct imaging in a binary system with bright stars, fast proper motion and limited observing windows is something else entirely. And then, after days of processing, something appeared, a faint blob of light, nestled near the masked-out position of Alpha Centauri A, separated by roughly 2 astronomical units, twice the Earth-Sun distance. Steady, persistent, not a cosmic ray hit, which would show up in only one frame. Not a background galaxy, which would have extended structure. Not a foreground asteroid, which would have moved between exposures. A point source. Sanghi stared at it. He ran the analysis again. He checked for instrumental artifacts, known issues with MIRI's detectors, optical ghosts, diffraction spikes from the coronagraph mask. Nothing matched. He cross-referenced the position against star catalogues, searching for a background star that might have aligned by chance with Alpha Centauri A. No match. He ran the subtraction algorithms differently, trying to make the signal disappear. It stayed. As a direct imager, Sanghi would later explain, you're always confounded by artifacts. You're very skeptical of anything you see. But this one, he said, just popped out so clearly. The brightness told them the mass. Infrared emission from a gas giant scales with its temperature and size. A planet roughly the mass of Saturn, 95 times Earth's mass, orbiting at 2 astronomical units from a sun-like star, would have cooled to about 225 Kelvin over 5 billion years. Negative 48 degrees Celsius. Cold enough that any methane in its atmosphere would begin condensing into clouds. Warm enough that hydrogen and helium would still dominate its composition. At that temperature, at that distance, with that orbital configuration, the planet should emit a specific amount of mid-infrared radiation, and the brightness of the blob matched. Not perfectly. There were error bars, uncertainties in the atmospheric models, unknowns about the planet's internal heat flow, but the match was close enough to be compelling. If the object was real, it was almost certainly a gas giant, roughly Saturn's mass, possibly Jupiter's size, orbiting in the habitable zone of the nearest sun-like star to Earth. The implications were immediate. If confirmed, this would be the closest directly imaged exoplanet ever detected, the nearest habitable zone world around a sun-like star, the oldest gas giant ever photographed, 5 billion years, compared to the tens or hundreds of millions of years typical for directly imaged planets around young stars. And it would be orbiting in a binary system where conventional planetary formation models suggested giant planets should not easily survive. Its very existence would challenge what we thought we understood about how planets form, migrate, and endure in gravitationally chaotic environments. But confirmation required one thing the team did not yet have: a second detection. The team did not celebrate. They did the opposite. They tried to destroy their own result. This is how science works when the stakes are high. You do not assume your detection is real. You assume it is wrong, and you spend weeks, months, trying to prove that assumption. You search for every possible way the signal could be an artifact, a mistake, a coincidence. You model the instrument, you simulate noise patterns, you cross-check against archival data from other telescopes. They tested whether the blob could be stray light from Alpha Centauri b, scattered into the field by imperfections in the chronograph. The geometry did not match. They tested whether it could be zodiacal dust, warm debris orbiting Alpha Centauri A, glowing in the infrared. The brightness was wrong. Dust would be diffuse, extended. This was point-like. They tested whether it could be a glitch in Miri's four-quadrant phase mask, a flaw in the coronagraph that created a false signal at that specific position. Other observations using the same mask showed no such feature. Every test came back negative. The signal remained. And that is when the team faced a choice. They could submit the result immediately, announce the detection, claim priority, publish fast, or they could wait, observe again, confirm the planet's motion, rule out the remaining uncertainties. They chose to wait. Webb observed Alpha Centauri A again in February 2025, then again in April. 2 more chances to see the planet. 2 more opportunities to measure its position, track its orbit, prove it was real. Both times the object was gone. The disappearance could mean 2 things. Either the planet was never real, the August detection was a fluke, a combination of noise and wishful thinking that happened to look like a planet for one brief observing window, or the planet was real but had moved. Orbital motion. The same force that makes planets predictable over centuries can make them invisible over months. If the planet follows an eccentric orbit, elongated, elliptical, swinging close to the star and then far away, it spends different amounts of time at different distances. And if that orbit is tilted relative to Earth's line of sight, the planet can appear to move toward or away from the star unpredictably, crossing in and out of regions where Webb's coronagraph can see it. The team ran simulations, millions of possible orbits. They constrained the models using the August detection, the 2 non-detections, and the 2019 observation from the Very Large Telescope that had hinted at something similar. They accounted for the gravitational influence of Alpha Centauri b, which would perturb any planetary orbit over time. The result? Roughly half of all stable orbits that fit the data would place the planet too close to Alpha Centauri A during the February and April observation windows. Too close to see, hidden in the glare, temporarily invisible, which means a non-detection does not disprove the planet, but it does mean we cannot confirm it yet. And that uncertainty, that gap between glimpse and proof, opens a deeper question. Not just whether the planet exists, but whether it should exist. A Saturn mass world orbiting a sun-like star in a tight binary system at an age of 5 billion years, in a stable orbit that somehow survived the chaotic early history of its formation. The physics of how such a planet could form there is not simple. It might not even be possible. Planet formation is simple, or at least it looks that way when you only study single stars. A young sun condenses from a collapsing cloud of gas and dust. The leftover material flattens into a disk. Particles stick together. Pebbles become boulders. Boulders become mountains. Mountains become embryonic worlds. Over tens of millions of years, gravity does the rest, sweeping up debris, clearing orbital lanes, sculpting a planetary system. We have watched this process happen, observed it with telescopes like ALMA, peering into stellar nurseries where protoplanetary disks glow with the heat of formation, modelled it with simulations that reproduce the basic architecture of our solar system. Rocky planets close in, gas giants farther out, debris belts at the edges. The physics is well understood. The timeline is predictable. The outcome, while variable, follows recognizable patterns. Except when there are 2 stars. Alpha Centauri is not a single star system. It is a binary. 2 suns locked in an 80-year gravitational dance, swinging from 11 astronomical units apart to 35 and back again, and that changes everything about how planets form. Picture this. You are trying to build a sandcastle on a beach. The sand is there, the tools are in your hands, but every few minutes a wave crashes over your construction site, scattering the grains you have carefully stacked. Some waves are small, some are catastrophic. You can rebuild after each one, but the structure is never stable for long. That is what planet formation looks like in a binary system. The problem starts with the protoplanetary disk itself, the reservoir of gas and dust from which planets must grow. In a single star system, that disk is calm. Particles orbit at predictable speeds, colliding gently, sticking together through electrostatic forces and weak gravity. But in a binary, the companion star acts like a cosmic egg beater. Every orbit, every close approach sends gravitational ripples through the disk, stirring the material, increasing collision velocities, turning gentle mergers into destructive impacts. Roman Rafikoff, a theoretical astrophysicist at the University of Cambridge, described the effect this way. A system like this would be the equivalent of a second sun where Uranus is, which would have made our own solar system look very different. Very different meaning, likely uninhabitable, possibly empty, perhaps never populated by planets at all. For a planet to form in a binary like Alpha Centauri, the building blocks, planetesimals, need to reach a minimum size before the companion star disrupts them. That minimum is 10 kilometers, not meters, not hundreds of meters. 10 full kilometers in diameter. Larger than Mount Everest is tall, massive enough that mutual gravity can hold them together through high-velocity collisions, big enough that the gravitational stirring from Alpha Centauri b cannot shatter them on impact. But how do you build a 10-kilometer object when the binary is actively preventing smaller pieces from sticking together? This is where the physics becomes precarious. One proposed solution is called the streaming instability, a process where drag forces in the gas disk cause solid particles to clump rapidly into dense concentrations that can collapse under their own gravity. It bypasses the slow, fragile stage of pebble-by-pebble growth. Instead, it jumps directly from dust grains to kilometre-scale bodies in a kind of runaway agglomeration. If streaming instability works in Alpha Centauri's chaotic disk, planet formation becomes possible. If it does not, the system remains barren. And here is the uncomfortable truth. We do not know which scenario applies. Streaming instability is still a theoretical model, elegant, mathematically sound, supported by simulations, but not yet confirmed observationally in any binary system. We have never watched it happen. We have only inferred that it might. Even if planetesimals reach 10 kilometers, even if they survive the companion star's gravitational stirring, even if they somehow grow into full-size planets over millions of years, there is still a final barrier. Orbital stability. A planet orbiting Alpha Centauri A cannot orbit too far from its star. The gravitational influence of Alpha Centauri B, swinging past every 80 years, sometimes as close as 11 astronomical units, perturbs any distant orbit. Computer simulations suggest the stability limit sits around 2 to 3 astronomical units. Beyond that, orbits become chaotic. Eccentricities grow. Planets either collide with their star, escape into interstellar space, or get captured by the companion. And if the planet's orbit is inclined, tilted more than 40 degrees relative to the binary's orbital plane, an even stranger effect takes hold, the Kozai mechanism. This is a three-body resonance where eccentricity and inclination trade places over time. A circular, highly inclined orbit becomes elliptical and flattened. An elliptical, low-inclination orbit becomes circular and steeply tilted. The planet oscillates between configurations, crossing through zones where it could collide with other planets or be ejected entirely. The Kozai timescale for Alpha Centauri is measured in thousands of years, not millions, thousands. A planet caught in this resonance would experience dramatic climate shifts, swinging from circular, temperate orbits to wildly eccentric, scorching, then freezing paths, faster than glacial cycles on Earth. You see the problem? The planet Webb detected, if it is real, sits at roughly 2 astronomical units, right at the edge of the stability zone. Its orbit is likely eccentric, based on the non-detections in February and April, and if simulations suggesting a 50-degree inclination are correct, it may be dancing on the edge of quasi chaos. It should not have survived 5 billion years in that configuration, and yet, if the signal is real, it did. This is where the story fractures into 2 incompatible possibilities. Either the models are wrong, planet formation in binaries is easier than we think, orbital stability extends farther than simulations suggest, and Saturn mass worlds can somehow endure in environments we believed were too violent to host them. Or the detection itself is wrong. The August 2024 signal was not a planet. The blob of light was instrumental noise or background contamination, or a transient phenomenon that mimicked a planetary signature for one brief observing window. Both options are uncomfortable. If the models are wrong, we have misunderstood something fundamental about how gravity operates in multi-star systems. Decades of theoretical work, simulations run by researchers at Cambridge, at the Max Planck Institute, at NASA's Jet Propulsion Laboratory, would need revision. The predictions we have made about which binaries can host planets, which habitable zones are stable, which systems are worth targeting with future telescopes, all of that would shift. If the detection is wrong, we face a different kind of failure. Webb pushed to its absolute limit. A custom observing sequence, months of data processing, teams at Caltech, at JPL, at the Space Telescope Science Institute, all working to extract a signal from one of the most challenging observations ever attempted. And the result? A phantom, a false positive, a reminder that even the most powerful telescope ever built can be fooled by the universe's noise. Neither conclusion feels satisfying, but there is a third possibility. The planet is real, and the models are incomplete. Not wrong, incomplete. Missing some mechanism, some pathway to stability, some process of orbital damping, some interaction between the gas disk and the forming planet that allows survival in regimes where current theory predicts destruction. If this is true, the implications ripple outward. Binaries make up more than half of all star systems in the galaxy. If planets can form and endure in tight binaries like Alpha Centauri, then the number of potentially habitable worlds in the universe increases dramatically. Habitable zones around binary stars are not as fragile as we thought. Rocky planets might exist where we never expected them. And the nearest example, the one that could teach us how this works, might be sitting just 4 light-years away, waiting for Webb to see it again. But confirming that requires more than one detection. It requires proof, repeated observations, orbital tracking, spectrum analysis, evidence that cannot be explained away as noise or artifact or wishful pattern matching in ambiguous data. And right now, we do not have that proof. What we have is a glimpse, a faint point of light that appeared once and vanished twice, a signal that fits the brightness of a Saturn mass world, but defies the stability models that should govern its existence. The question is not just whether the planet exists, the question is whether it should. There is a peculiar silence that settles over a research team when data arrives and shows nothing. Not error messages, not instrument failures, not corrupted files or misaligned pointing, just absence. The field is clear. The star is visible. The coronagraph worked perfectly. The subtraction algorithms ran without issue. The signal to noise is excellent. Everything functioned exactly as designed, and the planet is gone. This is what happened in February 2025 when Webb observed Alpha Centauri A for the second time. The same telescope, the same instrument, the same coronagraph mask placed over the same star, the same data reduction pipeline applied to the same type of raw images. The observation was granted under Director's discretionary time, a category reserved for urgent, high-priority targets that cannot wait for the normal proposal cycle. The August detection had been compelling enough to justify immediate follow-up. If the planet was real, every additional observation would refine its orbit, constrain its mass, build the case for confirmation. But when the processed images came back, the faint blob of light that had appeared so clearly in August was simply not there. The team checked for errors, reprocessed the data, examined the pointing logs to confirm Webb had been aimed at the correct coordinates. Everything was correct. The observation had worked. There was just nothing to see. Then, in April 2025, they tried again. Same result. No planet. How do you lose a Saturn-mass world orbiting the nearest Sun-like star to Earth? This was not a faint signal fading below the noise threshold. This was a complete disappearance, from clear detection in August to total absence in February and April. The kind of vanishing act that should not happen with objects that obey the laws of gravity and orbital mechanics. 3 scenarios seem possible. First, the August detection was never a planet. It was noise. A statistical fluctuation. An artifact produced by some combination of instrumental effects, stellar glare, and background contamination that happened to look exactly like a planetary signal for one observing window. The February and April non-detections proved it was never real. Second, the planet was real, but something destroyed it between August and February. A catastrophic collision, a sudden orbital instability, a plunge into the star or ejection into interstellar space. The planet existed briefly, then ceased to exist. Third, the planet was real, is still real, but has moved somewhere Webb cannot see it. The first scenario was plausible but frustrating. The second scenario was dramatic but statistically unlikely. Planetary systems do not spontaneously disintegrate on timescales of months. The third scenario was the most unsettling because it required the planet to be playing a game of cosmic hide-and-seek, and we had no way of knowing when it would reappear. Aniket Sanghi, staring at the empty field in the February data, said it plainly. We are faced with the case of a disappearing planet. Imagine you are standing in a large field at night, holding a flashlight. A friend stands 200 feet away, holding a candle. You can see the candle flame clearly, a faint point of light against the darkness. Now imagine your friend starts walking, not away from you, not toward you, but in a slow circle around a bonfire burning between you. When they are to your left or right, perpendicular to the bonfire, you can still see the candle. But when they move behind the bonfire, the flame disappears. Not because the candle went out, not because it got dimmer, because the bonfire's overwhelming light drowns it completely. This is what happens to planets in elliptical orbits around bright stars. When the planet is far from the star, at aphelion, the farthest point in its orbit, it appears separated by a large angular distance on the sky. Webb's coronagraph can block the star while leaving the planet visible. But when the planet swings close to the star, at perihelion, the nearest point, it moves inside the coronagraph's inner working angle. The star's residual light, the diffraction spikes, the scattered photons leaking around the mask's edges, all of that overwhelms the planet's faint thermal glow. The planet becomes invisible, not gone, just hidden. For a planet on a highly eccentric orbit around Alpha Centauri A, swinging from 1 astronomical unit at closest approach to 2 astronomical units at its farthest point, the visibility window is narrow. Webb can only see it when it is near aphelion, and that configuration occurs during specific months of the planet's multi-year orbit. The team ran simulations, millions of possible orbits. They constrained the models using 3 data points: the 2019 detection from the Very Large Telescope, the August 2024 detection from Webb, and the 2 non-detections in February and April. They required the orbits to be gravitationally stable. The planet could not be in a configuration where Alpha Centauri b would eject it over time. The result? Roughly half of all allowed orbits placed the planet too close to Alpha Centauri A during the February and April observation windows. 52% to be precise, which means that a non-detection in those months does not disprove the planet's existence. It actually fits the hypothesis that the planet is real, eccentric, and currently hidden in the star's glare. Here is what makes the disappearance so clean. There was no evidence of anything else. If the planet had been destroyed, shattered by a collision, torn apart by tidal forces, vaporized by an impact, there would be debris, dust, a glowing cloud of pulverized rock and ice expanding outward from the impact site. Webb's infrared detectors are exquisitely sensitive to warm dust. Even a small amount would produce a detectable signal. There was none. If the planet had plunged into Alpha Centauri A, there would be spectroscopic signatures, metals polluting the star's photosphere, excess infrared emission from heated materials spiraling inward, changes in the star's brightness or spectral lines as the planet's atmosphere burned away. Nothing. The star looked the same in February and April as it had in August. The surrounding environment showed no signs of recent disruption, no excess thermal emission, no circumstellar dust ring, no anomalous features in the background field. The planet simply was not there, which left only one explanation that fit all the data: geometry. The planet had moved. Its elliptical orbit had carried it from a visible position in August to an invisible position in February, and it remained invisible through April. Not destroyed, not ejected, just temporarily hidden behind the overwhelming brightness of its parent star. You can test this yourself with nothing more than patience and orbital mechanics. If the planet follows a 2 to 3 year orbit, it should reappear in August 2026. Same telescope, same star, same coronagraph. If the simulations are correct, the planet will have swung back out to aphelion by then, separating itself from the star by enough angular distance to become visible again. If Webb points at Alpha Centauri A in August 2026 and sees the same faint thermal point source it detected in August 2024, the planet is real. If it sees nothing, the August detection was a phantom. The emotional arc of this discovery has not followed the usual trajectory. Normally, a detection leads to confirmation. Excitement builds as follow-up observations refine the signal, sharpen the parameters, turn a candidate into a confirmed planet. Teams publish papers, press releases go out, the discovery enters the catalogue. Another world added to humanity's growing census of exoplanets. But this discovery has moved in the opposite direction, from detection to absence, from clarity to ambiguity, from a faint but definite signal to a deepening mystery that cannot be resolved without more time, more observations, more patience. The planet, if it exists, is not cooperating with our need for certainty, and that resistance, that refusal to be easily confirmed or easily dismissed, has transformed the story from a straightforward discovery into something more complex. This is no longer just about whether a Saturn-mass world orbits Alpha Centauri A. It is about the limits of observation, the challenges of studying objects that move in and out of visibility, the uncomfortable reality that even with the most powerful telescope humanity has ever built, aimed at the nearest sun-like star in the galaxy, we can still be left with questions instead of answers. Sankey and his team are not celebrating, they are calculating, running models, predicting when the planet should reappear, planning the next observation window, waiting. Because in astronomy, sometimes the most important discoveries are the ones that refuse to be simple, and sometimes the vanishing act is part of the story. Every astronomer who searches for planets knows the same uncomfortable truth. Most of what you see is not real, not galaxies, not planets, not new worlds waiting to be discovered. Just noise, light scattered by imperfect optics, thermal glow from the detector itself, residual starlight leaking around the coronagraph's edges. diffraction spikes, background contamination, cosmic rays striking the sensor, 1,000 different sources of false signal, all conspiring to look exactly like the thing you are searching for. Aniket Sanghi put it plainly, as a direct imager, you're always confounded by artifacts. You're very skeptical of anything you see. This is the central problem of exoplanet detection. You are trying to find something 10,000 times fainter than a star, hidden in the star's overwhelming glare, using instruments that are never perfectly calibrated through an atmosphere, or, in Webb's case, through space that is never perfectly still. Every pixel in the image carries uncertainty. Every point of light could be real, or it could be an illusion manufactured by the machinery itself. So, when a faint blob appeared in the August 2024 observation of Alpha Centauri A, the first question was not, "What is this planet like?" The first question was simpler, harder, more fundamental. Is this actually a planet at all? Imagine you were trying to photograph a firefly hovering next to a searchlight. The searchlight is 1,000,000 times brighter than the firefly. You cannot turn the searchlight off. You cannot move it. You cannot ask the firefly to hold still. And your camera, no matter how expensive, no matter how carefully engineered, bends light in ways that create ghost images, lens flares, reflections that look almost identical to the real firefly. This is direct imaging of exoplanets. The star is the searchlight, the planet is the firefly, and your camera is the most advanced space telescope humanity has ever built, operating at the absolute edge of what physics allows. Webb's coronagraph can block Alpha Centauri A's direct light, but blocking is not the same as removing. Light diffracts around the edges of the mask. Photons scatter off dust particles inside the telescope. The mirror's segmented structure creates interference patterns, bright spokes radiating outward from where the star should be, each one capable of hiding or mimicking a planetary signal. Then there is Alpha Centauri B, the second star, also bright, also close. Webb can block one star but not two simultaneously. B's light floods the detector, creating additional noise, additional artifacts, additional false signals that must be subtracted, modelled, removed. The team needed to prove that the faint point source they detected, labelled S1, was not an artifact of this optical chaos. The validation process begins with elimination. First, background objects, galaxies, distant stars lying billions of light years behind Alpha Centauri, appearing aligned by pure chance. Webb cannot tell the difference between a nearby planet and a faraway galaxy just by looking at brightness. Both appear as faint points of light, but galaxies do not move. Planets do. If S1 were a background object, it would remain stationary relative to Alpha Centauri A over months or years. The star moves, it has proper motion, drifting slowly across the sky as our solar system and Alpha Centauri orbit the galactic center at different speeds. A real planet orbiting the star would move with it. A background galaxy would not. The team checked. S1 is not stationary. It tracks with Alpha Centauri A's motion through space, not a background object. Second, foreground objects. Asteroids in our own solar system, crossing through the field of view during the observation. These appear and disappear on timescales of hours or days, leaving trails as they move against the background stars. S1 did not move like an asteroid. It appeared at a fixed position, relative to the star, not in our solar system. Third, instrumental artifacts. This is the hardest category to rule out, because Webb's optics create complex repeating patterns of false light, speckles, diffraction rings, residual glare bleeding around the chronograph mask. Any of these could, in principle, mimic a planetary signal in a single observation. To eliminate this possibility, the team did something clever. They observed a different star, a reference star with similar brightness but no companion, no binary partner complicating the field. They placed this star behind the coronagraph, exactly as they had done with Alpha Centauri A. Then they observed it again without the coronagraph. By comparing these two observations, they created a map of how light flows through Webb's optical system, how photons scatter, where diffraction spikes appear, what the instrument does to starlight when it tries to block it. They used this map as a template, a model of the noise. Then they subtracted that noise from the Alpha Centauri images, both the contribution from Alpha Centauri A and the overwhelming light from Alpha Centauri B. What remained, after all the subtractions, all the modelling, all the careful removal of known instrumental effects, was S1. Still there, still visible. A faint thermal glow separated from the star by 2 astronomical units. Not an artifact, or at least unlikely to be one. Here is the problem. Unlikely is not the same as impossible. The team performed extensive analysis. They ran simulations. They tested different subtraction algorithms. They checked for correlations with known instrumental effects. They compared S1's brightness, position, and thermal signature against thousands of previously imaged exoplanets and artifacts. Everything pointed toward S1 being real, a planet, a Saturn mass world on an eccentric orbit around the nearest sun-like star to Earth. But they could not prove it. Not definitively. Not yet. Why? Because they only saw it once. In science, particularly in astronomy, a single detection is never sufficient. Extraordinary claims, and a gas giant orbiting Alpha Centauri A is an extraordinary claim, require extraordinary evidence. That means repeated observations, independent confirmation. Watching the object move over time, following its orbit, measuring changes in brightness or position that match theoretical predictions. The February and April non-detections complicated the situation. If S1 were an artifact, a quirk of the August observation, a transient instrumental glitch, a statistical fluctuation in the noise, then its absence in later observations would make sense. Artifacts do not persist. They flicker into existence and vanish. But if S1 were a real planet on an eccentric orbit, its absence would also make sense. The simulations showed that 52% of allowed orbits would place the planet too close to the star during the February and April windows, rendering it invisible. 2 hypotheses, both consistent with the data, both plausible. No way to distinguish between them without more observations. This is the frustration of incomplete evidence. You have a signal. You have performed every test you can think of. You have ruled out most false positives. And yet, uncertainty remains. The planet might be real, or it might be an illusion created by noise, geometry, and the limitations of even the best instruments we can build. Charles Beischmann, looking at the August detection and the subsequent non-detections, emphasized the point carefully. With only a single robust sighting, the candidate could not be unambiguously confirmed as a bona fide planet, without follow-up observations to track its motion. There is a specific word astronomers use when they are not certain. Candidate, not planet. Candidate planet, not detection. Candidate detection. The word carries weight. It acknowledges both the strength of the evidence and the possibility of error. S1 is a candidate because the data support its existence but do not yet prove it. The thermal signature is consistent with a Saturn mass planet at 2 astronomical units. The position tracks with Alpha Centauri A's proper motion. The object is not a background star, not a foreground asteroid, not an obvious instrumental artifact. But not obvious is different from impossible. And in a field where false positives have burned researchers before, where the history of Alpha Centauri is littered with claimed planets that later vanished under scrutiny, caution is not optional. It is essential. The scientific method does not reward confidence, it rewards rigor, and rigor demands that you hold your conclusions lightly, until the evidence becomes overwhelming. Right now, the evidence for S1 is strong but not overwhelming, compelling but not conclusive, suggestive but not definitive. The planet might exist. The August observation might be the first confirmed detection of a world orbiting the star next door, or it might not. And until Webb points at Alpha Centauri A again in August 2026, until the simulation's predictions can be tested, until S1 either reappears or stays absent, until orbital motion either confirms or refutes the hypothesis, we are left in a state of productive uncertainty. The kind of uncertainty that does not paralyze, the kind that motivates, the kind that says, we have seen something. We do not yet know what it is, but we know how to find out. We wait, we plan, we observe again, and we let the universe answer. August 2024. The data processing completes. The subtraction algorithms finish running, and there, in the residual image after all known sources of light have been removed, sits a faint point source. S1, a dot of infrared thermal emission. Separated from Alpha Centauri A by 1.5 arcseconds, roughly 2 astronomical units in projected distance. Exactly where a planet could exist, but also exactly where an artifact could appear. The team knows this. They have seen false detections before. Speckles that look planetary, noise patterns that mimic thermal signatures, residual starlight that concentrates into bright spots through some quirk of the optical system. Every direct imager carries the same occupational hazard, seeing things that are not there. Sankey stares at the image. S1 is clear, distinct, brighter than the noise floor, positioned away from obvious diffraction features. But something about the observation bothers him. The August epoch had only one successful observation at a single roll angle, meaning Webb pointed at Alpha Centauri with its instruments oriented in only one direction. Normally, to confirm that a detection is real and not an artifact, you observe the same target with the telescope rolled to different angles. Instrumental artifacts stay fixed to the detector. Real astronomical objects stay fixed to the sky. By rotating the telescope and watching how the signal moves, or does not move, you can distinguish between machinery and cosmos. They did not get that luxury. Technical issues, observing constraints, the vagaries of scheduling a telescope shared by hundreds of research programs. One roll angle, one observation, one chance to see whether S1 was real, and now, months later, it has vanished. Here is where the story becomes strange. In 2019, 5 years before Webb's detection, a different telescope saw something at Alpha Centauri A. The Very Large Telescope in Chile, using a newly developed mid-infrared imaging system called NEAR, detected a faint point source at approximately 1.1 astronomical units from the star. The team called it C1, Candidate 1. C1 was never confirmed. The observation arc was too short, only 100 hours. Not enough time to track orbital motion. Not enough data to rule out dust, artifacts, or transient phenomena. The detection hovered in a scientific limbo, compelling but inconclusive, interesting but unproven. Now, 5 years later, Webb detects S1 at 2 astronomical units. On the opposite side of the star, 2 detections, 2 different telescopes, 2 different distances. Same star. Coincidence? Or the same planet, seen at 2 points in its orbit. The team faced a decision. They could treat S1 and C1 as separate objects, perhaps 2 planets orbiting Alpha Centauri A, or perhaps 1 real planet and 1 artifact. Or they could combine the observations, assume S1 and C1 are the same object, and use both data points to constrain a single orbit. They chose the latter. S1 plus C1, a combined candidate. 1 hypothetical planet observed twice over 5 years, appearing first at 1.1 astronomical units in 2019, then at 2 astronomical units in 2024. If this interpretation is correct, the planet follows a highly eccentric orbit, swinging close to the star, then far away, then close again. The eccentricity would be roughly 0.4, moderate, not extreme, but enough to create large variations in distance and visibility over the course of each orbit. But if this interpretation is wrong, if S1 and C1 are not the same object, then the entire orbital analysis collapses. Eccentric orbits complicate detection. Highly inclined orbits make it worse. The simulations suggest the planet, if it exists, orbits at an inclination of roughly 50 degrees relative to the Alpha Centauri AB orbital plane, or possibly 130 degrees, depending on whether the orbit is prograde or retrograde. 50 degrees is steep, very steep. Most planets in our solar system orbit within a few degrees of the ecliptic plane. Jupiter's inclination is 1.3 degrees. Saturn's is 2.5. Even Pluto, famously tilted, sits at 17 degrees. 50 degrees means the planet's orbit is sharply tilted relative to the binary system that shaped it. This is unusual, not impossible. Planets around binary stars can have tilted orbits due to gravitational perturbations, resonances, or migration events early in the system's history. But unusual enough to raise questions. Why would a planet form with such high inclination? What mechanism tilted it? And if the inclination is really 50 degrees, why did previous radial velocity searches, which measure the star's wobble caused by an orbiting planet, fail to detect it? High inclination reduces radial velocity signals. A planet orbiting edge-on produces maximum wobble. A planet orbiting face-on produces almost no wobble. At 50 degrees, the signal would be weakened but not eliminated. Saturn mass planets should still be detectable, particularly at the distances suggested by the S1 plus C1 orbit. And yet, no radial velocity detection has been reported. This creates another uncomfortable possibility. The planet might not exist at all. What if S1 is not a planet? What if it is an optical ghost, a phantom created by the complex interplay of starlight, coronagraph masks, and detector imperfections? Webb's optics are exquisite but not perfect. The primary mirror consists of 18 hexagonal segments, each aligned to nanometer precision, but still producing diffraction patterns that radiate outward from bright sources. The coronagraph blocks the star's direct light, but scattered photons leak around the mask's edges, creating residual glow that must be subtracted through modelling. Alpha Centauri b adds another layer of complexity. Its light floods the detector, creating its own diffraction pattern, its own scattered glow. The team subtracted this using a reference star, observing a different star with similar brightness, to create a template of how light behaves in Webb's optics. But subtraction is never perfect. Small errors in the model, minor misalignments in the template, subtle changes in the telescope's thermal state. Any of these could leave residual light that concentrates into a point-like feature, a feature that looks exactly like a planet. The February and April non-detections support this hypothesis. If S1 were an artifact tied to specific observing conditions, the telescope's orientation, the thermal environment, the exact geometry of Alpha Centauri A and B during the August observation, it might appear once and never again. Artifacts do not follow orbits. They do not obey Kepler's laws. They flicker into existence when conditions align, then vanish when those conditions change. But the hypothesis has problems. The team tested extensively for instrumental artifacts. They compared S1's position against known diffraction features. They checked for correlations with detector effects, thermal variations, pointing drift. They found none. S1 appeared in a location where no obvious instrumental signature should exist. And then there is C1. If S1 is an artifact, what was C1? A different artifact from a different telescope 5 years earlier. Two unrelated optical ghosts appearing at the same star by pure coincidence. Possible, but unlikely. This is the trap the team finds itself in. Neither hypothesis, planet, or artifact can be conclusively proven or disproven with current data. If S1 is a planet on a highly eccentric, highly inclined orbit, the August detection and the February and April non-detections all make sense. The simulations show 52% of allowed orbits would hide the planet during those months. Orbital motion explains everything. If S1 is an artifact, its single appearance and subsequent absence also make sense. Optical ghosts do not persist across observations. Instrumental noise fluctuates. The complexity of subtracting two bright stars from a crowded field creates ample opportunity for false positives. Both stories fit the data. Both have explanatory power. And crucially, both are plausible enough that scientists cannot simply dismiss one in favor of the other. The S1 plus C1 hypothesis strengthens the planetary interpretation. Two independent telescopes seeing faint thermal sources at Alpha Centauri A over a 5-year span is harder to explain as coincidence, but combining the detections introduces new assumptions. That C1 was not itself an artifact, that the two sources are genuinely the same object, that the orbital parameters derived from just two data points are accurate. Each assumption carries risk. Each one could be wrong. You see the problem. The evidence is strong enough to be compelling, but not strong enough to be conclusive. The planet might be real, or it might be a ghost, a phantom born from the machinery of observation, from the difficulty of separating faint signals from overwhelming noise, from the fact that even our best instruments struggle when pushed to their absolute limits. August 2026 will provide an answer. If the orbit simulations are correct, S1 should reappear. Same star, same separation, moving along the predicted path through space. If it appears, the ghost becomes real. If it does not appear, the ghost remains a ghost. Until then, we are left with ambiguity. The kind that does not resolve easily, the kind that forces you to hold two incompatible possibilities in your mind at once, weighing probabilities, questioning assumptions, waiting for the universe to clarify what our instruments have shown us. This is not failure. This is the scientific method working exactly as designed, proposing hypotheses, testing predictions, refusing to claim certainty when uncertainty still exists. But it is uncomfortable nonetheless, because somewhere in the data, buried in the photons that travelled 4.3 light-years from Alpha Centauri to Earth, is the truth. Either a planet orbits our nearest stellar neighbour, or it does not. Either we saw it, or we saw a ghost. And right now, we genuinely do not know which. There are places in the sky where planets can hide, not behind other worlds, not in the shadows of moons or rings, but in something more fundamental, in the overwhelming brightness of their own stars, in zones where the parent sun's glare is so intense that even the most sensitive instruments cannot distinguish a planet's faint thermal glow from the flood of stellar photons scattered by imperfect optics. These zones exist around every star, circles of invisibility, regions where planets can orbit unseen, not because they cease to exist, but because observation becomes impossible. The star's light drowns everything within a certain angular radius, typically measured in fractions of an arc-second, creating a blind spot at the very center of every planetary system we try to image. For Webb's coronagraph observing Alpha Centauri A, that blind spot extends roughly 0.7 arc-seconds from the star. In physical distance, at Alpha Centauri's range of 4.3 light-years, this translates to approximately 1 astronomical unit. Anything closer than that becomes undetectable. The chronograph mask blocks the star's direct light, but residual glare, photons diffracting around the mask's edges, scattering off the telescope's mirrors, leaking through imperfections in the optical system, creates a bright halo, a zone of confusion where even Saturn-mass planets disappear. This is where S1 went. The boundary between visible and invisible is called the inner working angle. Every coronagraph has one. It defines the minimum separation at which a companion, planet, brown dwarf, or stellar companion, can be distinguished from the central star. For Miri's coronagraph, the inner working angle is approximately 0.7 arcseconds. Objects farther than this can be detected, provided they are bright enough. Objects closer than this vanish into the star's residual glare, no matter how luminous they are. But planets do not remain stationary. They orbit. And if that orbit is eccentric, elongated rather than circular, the planet's distance from the star changes dramatically over time. Imagine a planet on a circular orbit. Its separation from the star stays constant. If it starts outside the inner working angle, it remains outside. Always visible, always detectable. Now imagine a planet on an eccentric orbit. At aphelion, the farthest point, it might sit at 2 astronomical units, well outside the coronagraph's blind spot. Easily visible, but as it swings toward perihelion, the closest approach, it moves to 1 astronomical unit or less. Inside the inner working angle, gone. This is what the simulations suggest happened to S1. The team's orbital models constrain S1 plus C1 to an eccentricity of roughly 0.4. Not the highest eccentricity known. Some exoplanets have eccentricities above 0.9, orbits so elongated they resemble comets more than planets, but high enough to create significant variation in distance. With an eccentricity of 0.4 and a semi-major axis around 1.6 to 2.1 astronomical units, the planet would swing from approximately 0.9 to 1.0 astronomical units at perihelion to roughly 2.3 to 3.4 astronomical units at aphelion. The August 2024 observation caught the planet near aphelion, far from the star, separated by enough angular distance to be visible. The detection was clean, clear, unambiguous. A faint thermal point source exactly where a Saturn mass world could exist. But by February 2025, the planet had moved. Orbital mechanics carried it inward toward perihelion. The simulations show it crossing inside the 1 astronomical unit threshold sometime between August and February, entering the zone where Webb's coronagraph can no longer resolve it from the star's glare. It remained there through April, hidden. Not because it vanished, not because it was destroyed or ejected, but because it moved to a location where our instruments cannot see. Orbital motion created the disappearance. Eccentric orbits tell stories about a planetary system's history. In our solar system, most planets orbit on nearly circular paths. Earth's eccentricity is 0.017. Jupiter's is 0.049. Even Mars, with the most eccentric orbit of the major planets, sits at 0.093. These low eccentricities reflect a calm formation environment, a protoplanetary disk that settled into stable, circular configurations over millions of years. But Alpha Centauri is not a single star. It is a binary, and binaries disrupt planetary formation. The gravitational influence of Alpha Centauri b, swinging past every 80 years, sometimes as close as 11 astronomical units, perturbs any planet orbiting Alpha Centauri A. It pumps eccentricity into the orbit, stretches circles, into ellipses. The 0.4 eccentricity of the S1 plus C1 candidate is exactly what you would expect from a planet shaped by binary dynamics. Not catastrophically high, which would suggest the planet is on the verge of instability, but elevated above the baseline you see in single-star systems, a signature of gravitational harassment by a stellar companion. And the inclination, 50 degrees relative to the Alpha Centauri AB orbital plane, reinforces this story. High inclination orbits are rare in isolation, but in binary systems they can arise from gravitational interactions that tilt planetary orbits out of the original disk plane. The Kozai mechanism, named after Japanese astronomer Yoshihide Kozai, describes how a distant companion can periodically exchange inclination and eccentricity in a three-body system. Over time, the orbit oscillates, becoming more eccentric and less tilted, then more tilted and less eccentric, cycling between configurations. If S1 is real, its orbital parameters are not just consistent with a binary system, they are shaped by one, molded by 5 billion years of gravitational influence from Alpha Centauri b. Every perihelion passage, every swing through aphelion, carrying the imprint of a second star's presence. This is what makes the detection compelling. The orbit, if accurately constrained, fits the environment. It does not defy the physics. It reflects it. The eccentricity and inclination allow prediction. If the S1 plus C1 orbit is correct, the planet follows a 2 to 3 year period around Alpha Centauri A. It appeared at aphelion in August 2024. It vanished into perihelion by February 2025, which means by August 2026, it should have completed roughly half an orbit and returned to aphelion, visible again, separated from the star. Outside the coronagraph's inner working angle, the team has calculated the expected position. They know where to point Webb. They know what brightness to expect. They know the thermal signature a Saturn-mass planet at that distance should produce in MIRI's 15.5 micrometer filter. August 2026 becomes a test, not just of whether S1 is real, but of whether the entire orbital framework, the eccentricity, the inclination, the semi-major axis, the period derived from combining two detections 5 years apart, is accurate. If the planet reappears where predicted, the case strengthens dramatically. Orbital motion confirmed, eccentricity validated. The hypothesis transforms from plausible to probable. If nothing appears, the interpretation collapses. Either the orbit is wrong, meaning S1 and C1 are not the same object, or S1 was never a planet, an artifact, a ghost, a false positive generated by the complexity of observing the brightest nearby stars with instruments pushed to their detection limits. This is the nature of prediction in astronomy. You propose a model. The model makes specific, testable claims about where objects will be at future times. Then you wait, and when the predicted time arrives, you observe. The universe either confirms your model or refutes it. No ambiguity, no second guessing, just observation matching prediction or failing to match it. For S1, that moment comes in roughly 1 year. A single observation in August 2026. One field, one coronagraph mask, one subtraction of stellar light, and either a faint point source appears at the predicted location or it does not. Until then, the planet, if it exists, orbits in the dark, hidden inside the zone where stars outshine everything, moving along an ellipse shaped by binary dynamics, tilted 50 degrees from the plane it was born in, cycling between visibility and invisibility as it swings between aphelion and perihelion, waiting to be seen again, or waiting to be proven a ghost. A gas giant in the habitable zone cannot support life. This is true. Saturn-mass worlds have no solid surface, no stable ground, no place for oceans to gather or continents to form. Their atmospheres are hundreds or thousands of kilometers deep, crushing pressure zones of hydrogen and helium, where temperatures rise from frozen methane clouds at the top to molten metallic states near the core. Nothing we would recognize as biology could survive there. No chemistry capable of self-replication. No metabolism that could extract energy from those conditions. The planet itself is uninhabitable, but a gas giant is not alone. Jupiter has 95 known moons. Saturn has 274. Uranus has 28. Neptune has 16. Every gas giant in our solar system is accompanied by a retinue of smaller worlds, some barely larger than mountains, others comparable to planets in their own right: Europa, Enceladus, Titan, Ganymede, moons with subsurface oceans, moons with thick atmospheres, moons with active geology, liquid water, organic chemistry, worlds that, despite orbiting gas giants far from the sun's warmth, maintain conditions where life might, in principle, exist. If the S1 candidate is real, it does not orbit alone either. A Saturn mass planet at 1.6 to 2.1 astronomical units from Alpha Centauri A sits squarely in the star's habitable zone, the region where temperatures allow liquid water to exist on a surface. The planet itself has no surface, but any moon large enough to retain an atmosphere, orbiting at the right distance from the gas giant, would receive enough stellar radiation to stay warm, not scorching, not frozen, temperate, the kind of temperature range where water remains liquid, where atmospheres can be stable, where, if the right chemistry exists, biology becomes possible. This is the moon hypothesis. A moon orbiting a gas giant in the habitable zone experiences two sources of heat. First, stellar radiation. Sunlight from Alpha Centauri A, warming the moon's surface, driving weather, powering photosynthesis if life exists. This is the same heat source that warms Earth. Second, tidal heating. Gravitational forces from the gas giant stretching and compressing the moon as it orbits, converting orbital energy into internal heat. This is the same mechanism that keeps Europa's subsurface ocean liquid despite orbiting Jupiter far from the sun's warmth. The combination creates environments unlike anything possible on planets orbiting alone. Imagine a moon the size of Mars, too small to retain a thick atmosphere through its own gravity if it orbited the sun directly. But orbiting a Saturn mass giant at Alpha Centauri, it gains stability. The gas giant's magnetosphere shields it from stellar wind. Tidal forces keep the interior geologically active, recycling nutrients, maintaining a magnetic field, driving volcanism that replenishes atmospheric gases lost to space. The moon could have oceans, continents, weather systems, plate tectonics, every condition necessary for complex surface chemistry, and it would be 4.3 light-years away, the nearest potentially habitable world to Earth. Not a planet, a moon. In 2009, James Cameron's film Avatar depicted a habitable moon called Pandora, orbiting a gas giant named Polyphemos in the Alpha Centauri system. Lush jungles, breathable atmosphere, bioluminescent ecosystems, indigenous intelligent life. It was fiction, imaginative world-building designed for cinematic spectacle, but it was not arbitrary fiction. Cameron consulted scientists. The physics of a large moon in Alpha Centauri's habitable zone is sound, the tidal heating, the magnetospheric protection, the stable climate buffered by a massive planetary companion. All of this could, in principle, exist, which creates a problem for scientists trying to communicate about the S1 candidate. The moment you mention habitable moons around a gas giant at Alpha Centauri, the comparison to Avatar becomes unavoidable. The science fiction reference overshadows the science, the speculation drowns the data, and suddenly, serious researchers discussing orbital dynamics and exomoon detection limits are being asked whether they have found Pandora. They have not. To be clear, no moon has been detected around S1. No atmosphere has been characterized. No biosignatures have been measured. The planet itself remains unconfirmed. Discussing what moons it might host, what conditions those moons might have, is extrapolation built on hypothesis built on a single debated detection. But the possibility is not scientifically unreasonable, and that distinction matters. Speculation without basis is imagination. Speculation grounded in physics is prediction. The moon hypothesis is the latter. It does not claim moons exist. It identifies what would be required to detect them if they do, and what their properties might be based on known planetary science. This is how science approaches uncertainty, not by refusing to think beyond confirmed data, but by delineating clearly where observation ends and inference begins. There is something deeply human about wanting life to exist at Alpha Centauri. Not just anywhere, not in some distant galaxy billions of light years away where confirmation is impossible and contact unimaginable, but here, next door. Close enough that the light travelling from that system to our eyes left only 4 years ago. Close enough that we could, with sufficient technology and resources, send probes within a human lifetime. Close enough to matter. We want the nearest stars to host worlds. We want those worlds to be habitable. We want habitable to mean inhabited. It is not a scientific impulse. It is an emotional one, a desire to not be alone in a universe that feels vast and empty. And that desire creates risk. The risk of seeing what we want to see rather than what the data shows. The risk of interpreting ambiguous signals as confirmation. The risk of building narratives, habitable moons, complex ecosystems, perhaps even intelligence, on foundations that have not yet been verified. The history of Alpha Centauri is littered with these narratives. Planets claimed and retracted, detections that vanished under scrutiny, hopes elevated, then disappointed. Each time the lesson is the same. Proximity breeds speculation, and speculation requires discipline. The moon hypothesis must be held lightly, acknowledged as possibility, explored through modelling and prediction, but never confused with observation, never treated as fact. Detecting an exomoon is extraordinarily difficult. The moon would be smaller than the planet, fainter, closer to the star's glare. Its thermal signature would be a fraction of the gas giant's already faint emission. Even if S1 is confirmed as real, even if future observations track its orbit and measure its mass precisely, resolving individual moons would require instruments beyond Webb's capabilities. It might require missions specifically designed for Alpha Centauri. Starshades flown in formation with telescopes, blocking starlight to unprecedented levels. Interferometers combining light from multiple spacecraft to achieve resolution impossible with single mirrors. Decades of technological development, billions in funding, international cooperation on scales rarely achieved. But if the planet exists, the question becomes unavoidable. Not, could moons exist? The physics says yes. But do they? And if they do, what are they like? These are answerable questions. Difficult, expensive, requiring patience and precision, but answerable. And that is what makes the moon hypothesis compelling. Not because it offers easy confirmation, but because it offers a path. A sequence of observations and missions that could, step by step, reveal whether the nearest gas giant to Earth hosts worlds capable of supporting life, or whether, despite proximity and favourable conditions, the system remains barren, lifeless, a reminder that habitability does not guarantee inhabitants. Either answer would be profound, either one would reshape how we think about our place in the cosmos. But to find out, we first need to confirm the planet, and for that, we return to August 2026. We expect science to deliver certainty. A question is asked, experiments are designed, data is collected, analysis is performed, and at the end, after all the careful work, all the peer review, all the validation, an answer emerges. Clean, definitive, final. This is how science is often presented. In textbooks, in press releases, in headlines declaring scientists discover or new study proves. The narrative arc is familiar. Mystery identified, investigation conducted, solution found, beginning, middle, end. But that is not how science works. Not really. Not when you are operating at the edge of what instruments can detect and theories can explain. Not when you are searching for faint signals in overwhelming noise. Not when the subject of your investigation is 4 light years away and refuses to cooperate with observation schedules. The story of S1, the the candidate planet that appeared, vanished, and might reappear, is not a story about answers. It is a story about process, about how science actually functions when pushed to its limits, about the uncomfortable space between we saw something and we know what it is. There are two versions of the Alpha Centauri story. The public version, Webb detects planet around nearest sun-like star, clear, exciting, definitive, a discovery announcement, evidence of a world next door, confirmation that our nearest stellar neighbour hosts planetary companions. The scientific version, candidate point source detected in August 2024, observation of Alpha Centauri A, non-detections in February and April 2025, consistent with eccentric orbital motion, further observations required for confirmation. Same data, different narratives. The gap between these versions reveals something fundamental about how science communicates uncertainty. The public wants discoveries. Science offers candidates. The public wants confirmation. Science provides probabilities. The public wants to know what exists. Science can only report what has been observed and what those observations might mean, and how confident we should be in those interpretations. This is not evasion. It is precision. When Bachmann's team published their results, they did not claim to have found a planet. They reported a detection. They described the validation process. They presented orbital models consistent with the data. They calculated the probability that follow-up non-detections could be explained by eccentric orbital motion, 52%, not 0, not 100, 52. That number, uncomfortable, ambiguous, right in the middle of the probability space, is what honest science looks like. Here is what we know about S1. August 2024. Point source detected. Brightness consistent with Saturn mass planet. Position approximately 2 astronomical units from Alpha Centauri A. Not a background object, not a foreground asteroid. Unlikely to be an obvious instrumental artifact. February and April 2025. No detection. Field empty. Star visible. Coronagraph functioning. Subtraction algorithms working correctly. Object absent. That is the data. Everything else, the eccentricity, the inclination, the orbital period, the connection to C1, the predictions for August 2026, is model, interpretation, hypothesis built on incomplete information. The models are not random. They are constrained by physics, by orbital mechanics, by the requirement that any proposed orbit must be gravitationally stable in the presence of Alpha Centauri B, by the need to explain both the August detection and the subsequent non-detections. But constrained is not confirmed. The models show what could be true if certain assumptions hold. They do not prove those assumptions are correct. This is the nature of scientific modeling. You build a framework that fits available data. You use that framework to make predictions, then you wait for new observations to either support or refute the model. The model is a tool, a working hypothesis, not truth, never truth. Just the best current explanation given limited information, and when new data arrives, the model changes. In 2012, astronomers announced the discovery of Alpha Centauri BB, a planet slightly more massive than Earth, orbiting Alpha Centauri B every 3.2 days. The detection used radial velocity measurements. The signal appeared in multiple data sets. The statistical significance crossed accepted thresholds. It was published, celebrated, added to exoplanet catalogues. By 2015, it was gone. Not the planet, the claim. Independent analysis showed the signal was an artifact of how the data had been processed. A quirk of stellar activity cycles. A false positive. The planet never existed. This could be viewed as failure, a mistake, embarrassment for the researchers involved. But it is not. It is science functioning correctly. The original team reported what they saw in the data. They applied standard analysis techniques, They reached a conclusion supported by the information available at that time. Then, other teams examined the same data with different methods, identified problems with the original analysis, and the claim was retracted. No cover-up, no defensiveness, just revision, correction, the willingness to say, "We were wrong" when the evidence demands it. This is not weakness. It is the only reason science produces reliable knowledge, because individual claims, no matter how carefully made, no matter how confident the researchers, are always provisional, always subject to re-examination, always open to being overturned by better data or better analysis. S1 might follow the same path, detected, modelled, predicted to reappear. Then, when August 2026 arrives, nothing. Empty field. The orbital model's wrong. The connection to C1 spurious. The candidate revealed as artifact or misinterpretation. If that happens, it will not mean the Bachmann team failed. It will mean they reported their observations honestly, proposed explanations that fit the data, and allowed those explanations to be tested. That is how science works. The story of Alpha Centauri has been unfolding for decades. False starts, claimed planets that vanished, observations that raised more questions than they answered. Each time, we learn something, if not about what exists at our nearest stellar neighbour, then about how to search, how to observe, how to distinguish signal from noise. S1 is the latest chapter, not the conclusion, the latest chapter. We do not yet know how it ends. Planet confirmed, planet refuted, new detections complicating the picture further. The narrative remains open, and that openness, that uncertainty, is not a flaw in the scientific process. It is the point. Science does not promise answers on demand. It promises a method for approaching questions, a framework for testing ideas, a commitment to following evidence wherever it leads, even when it leads to "we don't know yet." The S1 candidate teaches us patience. It teaches us humility. It reminds us that proximity does not guarantee clarity, that even the nearest stars keep secrets, that the universe reveals itself slowly and only to those willing to wait. August 2026 will bring data. That data will support the orbital models or contradict them. Either outcome advances knowledge. Either one moves the story forward. Because science is not a collection of answers. It is a process of asking better questions. And right now, at Alpha Centauri, the questions are just beginning. The observation window opens in August 2026. Webb's scheduling committee will allocate time. The team will submit their proposal, pointing coordinates, exposure duration, filter selection, coronagraph configuration, every parameter calculated to capture S1, if it exists, at the predicted position in its orbit. The observation itself will take hours, maybe a full day, accounting for telescope slews, calibration frames, reference star observations. Data will flow from Webb's detectors to the deep space network antennas scattered across Earth. Raw photons encoded, transmitted, received. Then processing begins. Weeks, perhaps months, of analysis. Subtracting starlight, modelling instrumental effects, searching the residual image for a faint thermal point source at 1.5 arcsecond separation. Either it appears, or it does not. That single observation, one pointing, one field, one moment in August 2026, carries the weight of 5 years of uncertainty. It is not the end of the story, but it is the next chapter, the pivot point where hypothesis becomes testable prediction, and we are already planning what comes after. Modern astronomy does not wait for results before designing the next observation. While Webb prepares for August 2026, another telescope is being assembled, the Nancy Grace Roman Space Telescope, named after NASA's first chief astronomer. Built around a 2.4-meter mirror, the same size as Hubble's, donated from a discontinued intelligence satellite program, scheduled to launch no later than May 2027. Roman carries 2 instruments: the Wide Field Instrument, a 300-megapixel camera designed to survey hundreds of millions of galaxies, map dark energy, find thousands of exoplanets through gravitational microlensing, and the coronagraph instrument, a technology demonstrator, an experimental system designed to push direct imaging beyond what Webb can achieve. Roman's coronagraph is different from Webb's, not passive, active, equipped with deformable mirrors that flex and adjust in real time, correcting for imperfections in the telescope's optics. Capable of achieving contrast ratios approaching 1 part per billion, starlight suppression better than any coronagraph ever flown, and it is specifically designed to observe binary stars, to handle exactly the kind of complex 2-star system that makes Alpha Centauri so challenging. The engineering team has run simulations, tested wavefront control algorithms, built lab prototypes demonstrating that Roman's multi-star wavefront control system can suppress light from both Alpha Centauri A and Alpha Centauri B simultaneously. If S1 is confirmed by Webb in 2026, Roman becomes the natural follow-up. Better contrast, better stability, better angular resolution at certain wavelengths. Not just detecting the planet, but characterizing it, measuring its spectrum, identifying atmospheric composition, determining whether it has rings, moons, weather patterns, and Roman is just one piece of a larger infrastructure being built specifically for nearby stars. This is how modern exoplanet science operates, not as isolated observations, but as coordinated campaigns spanning years, telescopes, wavelengths. Step 1. Detection. Webb sees S1 in August 2024. Faint, ambiguous, requiring follow-up. Step 2. Validation. February and April 2025 observations, non-detections that complicate rather than clarify, forcing orbital modeling, probability calculations, interpretation debates. Step 3. Confirmation. August 2026. Testing the prediction, observation that either supports or refutes the orbital hypothesis. Step 4. Characterization. If confirmed, Roman observes in 2027 or 28. Spectroscopy. Photometry across multiple wavelengths, building a physical model of the planet's properties. Step 5. Long-term monitoring. Tracking orbital motion over years, measuring period, eccentricity, inclination precisely. Searching for additional planets, looking for moons, watching for variability that might indicate weather, rotation, seasonal changes. Each step depends on the previous. Each one builds knowledge incrementally. And critically, each one takes time, years between observations, months between data collection and publication. The cycle moves at the pace of orbital mechanics, telescope scheduling, peer review, budget allocations. This frustrates the public appetite for certainty. Discovery announcements are expected to be final, definitive. But in reality, astronomical discoveries unfold slowly. What appears as a sudden breakthrough, Webb detects planet at Alpha Centauri, is actually the beginning of a process that might take a decade to complete. And even then, confirmation is never absolute, just progressively more. Confident. Here is what makes Alpha Centauri different from every other exoplanet target. Distance, 4.3 light-years, 25 trillion miles. In cosmic terms, nothing, a distance so small that it changes what is possible. If a gas giant exists at Alpha Centauri A, if S1 is confirmed, characterized, studied, it becomes the nearest exoplanet system to Earth, capable of hosting potentially habitable moons. Not the most Earth-like, not the most likely to harbor life, but the nearest, and nearness matters in ways that go beyond scientific convenience. A planet at Alpha Centauri could be reached by spacecraft traveling at 10% the speed of light in roughly 40 years. Fast enough that a mission launched today could arrive within a human lifetime. Fast enough that you, if you are young enough, might live to see the first close-up images of a world orbiting our nearest stellar neighbour. This is not science fiction speculation, it is engineering extrapolation. The Breakthrough Starshot initiative has already outlined designs for laser-propelled light sails capable of reaching relativistic speeds. The technology does not exist yet, but the physics is sound. The challenges are engineering problems, not fundamental impossibilities. A confirmed planet at Alpha Centauri changes the calculus of interstellar exploration. It provides a target, a destination that is close enough to be relevant, a place where probes could arrive and transmit data back to Earth in less than a century. You might not live to see those images, but your children might. Your grandchildren almost certainly would. That proximity, that tantalizing closeness, transforms a detection from abstract science into something personal. This is not a planet orbiting a star thousands of light years away, so distant that it will never be more than a data point. This is a world next door, a place that could be visited, studied, known in detail, if it exists. Between now and August 2026, nothing changes at Alpha Centauri. The planet, if real, continues its orbit, swinging from perihelion to aphelion, moving through space at speeds dictated by gravity and orbital mechanics, indifferent to whether we observe it, unconcerned with our telescopes, our models, our uncertainties. The universe does not care about our desire for answers, but we wait anyway. We plan observations, we build better instruments, we refine our questions, because that is what humans do when faced with mystery at the edge of the known. August 2026 is not far away, but the candidate remains in limbo, neither confirmed nor refuted, neither planet nor artifact, existing in the uncomfortable space between detection and knowledge, and we, those of us watching this story unfold, are left with questions that have no answers yet. Questions that can only be resolved through patience, through observation, through the slow, methodical process of science, operating at the limits of what instruments can detect. The next chapter of this story is already written. The observations are planned, the timeline is set. We just have to wait for the universe to reveal it. We have travelled a long way together, through the complexities of binary star dynamics, through the physics of orbital eccentricity and inclination, through the frustration of detections that appear and vanish, through the careful, patient process of science working at the absolute edge of what our instruments can reveal. And we have arrived here, at the end of this story. Except it is not really the end, is it? The story continues at Alpha Centauri whether we are watching or not. There is a particular kind of loneliness that comes from seeking something very close and finding only questions, not answers, not certainty, just questions that multiply the more carefully you look. This is what Alpha Centauri offers us, the nearest sun-like star system to Earth. Close enough that its light, travelling at the fastest speed the universe allows, reaches us in 4 years. Close enough that we can resolve its companion stars. Close enough that we built the most powerful telescope humanity has ever launched specifically to search for worlds there. And what did we find? A faint point of light, detected once, absent twice, consistent with a Saturn-mass planet on an eccentric orbit, also consistent with an optical artifact, also consistent with noise that briefly resembled signal. We found uncertainty. Let us be clear about what we know and what we do not. In August 2024, Webb's mid-infrared instrument detected a thermal point source at Alpha Centauri A. The object appeared approximately 2 astronomical units from the star. Its brightness matched what you would expect from a gas giant, with a temperature of around 225 Kelvin. Analysis ruled out background galaxies, foreground asteroids, and many obvious instrumental artifacts. The detection was real in the sense that photons arrived at Webb's detector and created a signal. Whether those photons came from a planet is a different question. In February and April 2025, Webb observed Alpha Centauri A again. The signal was gone. The field was empty. Not dimmer, not relocated. Gone. Orbital simulations show this disappearance is consistent with a planet on an eccentric orbit, moving inside the chronograph's inner working angle. 52% of gravitationally stable orbits fitting the August detection and the 2019 VLT observation would hide the planet during the February and April windows. This is not proof. It is consistency. The data does not contradict the planetary hypothesis, but neither does it confirm it. August 2026 will provide the next test. If the planet exists, if the orbital models are correct, it should reappear. Visible again. Separated from the star. Detectable. And if it does not appear, then the August 2024 signal was something else. An artifact. A false positive. A reminder that even our best instruments can be fooled by the complexity of observing the brightest nearby. Stars. Both outcomes are possible. Both remain plausible. The universe has not yet chosen which story to tell. There is something deeply human about wanting the nearest star to host planets. Not just any planets, habitable ones, or at least planets with habitable moons, worlds where conditions might allow life, places that could, in principle, be visited by spacecraft launched within our lifetimes. We want our cosmic neighborhood to be populated. We want to look at Alpha Centauri, visible to anyone in the southern hemisphere as a bright point of light marking the foot of the Centaur, and know that worlds orbit there, that we are not alone even in the small sphere of space immediately surrounding our sun. But the universe does not organize itself around human desires. The fact that Alpha Centauri is close does not make it more likely to host planets. Proximity is an accident of galactic geography. The stars that ended up nearest to us were not chosen for their planetary potential. They are simply the ones that happen to form in this region of the Milky Way's spiral arm, whose random motions through the galaxy brought them close to our solar system's current position. Alpha Centauri owes us nothing, not planets, not answers, not confirmation of our hopes. And yet we search anyway, because proximity changes what is possible, even if it does not change what is probable. A planet at Alpha Centauri, if confirmed, becomes reachable in ways that planets around distant stars never will be. It becomes a destination, a place that future generations might visit. That possibility justifies the effort, the years of observation, the custom telescope sequences, the careful modelling and analysis, the patience required to wait for orbital mechanics to bring a hidden world back into view. We search because we can, because the tools exist, because the star is close enough that the attempt is meaningful. The story of S1 teaches us something about knowledge itself. We live in an era where information feels instant. Questions typed into search engines return answers in milliseconds. News breaks in real time. Communication spans the globe at the speed of light. We have grown accustomed to certainty on demand. But the universe operates on different timescales, and some questions, particularly questions about faint objects orbiting distant stars, cannot be answered quickly. They require patience, repeated observations, years of data collection, the willingness to sit with uncertainty while evidence accumulates slowly. S1 might be a planet, it might not. And for now, both possibilities must be held simultaneously. Not because the science is incomplete, though it is, but because this is how discovery actually works when you are operating at the limits of observation. The August 2024 detection was not a failure. It was a data point, a piece of evidence that raised more questions than it answered. Those questions led to predictions, orbital models, testable hypotheses about where the planet should be at future times. Now we wait to see if those predictions hold. This is not weakness, it is rigor, the refusal to claim certainty when uncertainty still exists, the commitment to following evidence wherever it leads, even when it leads through years of ambiguity. Science is not a collection of facts, it is a process, a method for approaching questions that cannot be answered by intuition or authority or wishful thinking. And sometimes, often, when the questions are hard enough, that process is slow. S1 reminds us that slowness is not failure. It is just the pace at which the universe reveals itself. Why do we do this? Why devote resources to searching for planets around other stars when we have so many problems here on Earth? Why build telescopes that cost billions of dollars to look at objects so faint they can barely be detected? Why care whether a point of light 4 light-years away is a planet or an artifact? The answer is not practical. We will not mine resources from Alpha Centauri. We will not colonize its planets in any foreseeable future. Confirming S1 would not solve climate change, cure diseases, or feed the hungry. The answer is something else, something harder to quantify, but no less real. We search because we are a species that asks questions about what lies beyond the horizon, because our minds are capable of wondering whether we are alone, because we can look at a point of light in the night sky and ask not just, what is that, but, are there worlds there? Could life exist on them? What would they be like? These questions have no survival value. They do not help us reproduce or acquire resources or compete with rivals. They are pure curiosity, the impulse to know for its own sake. And that impulse, that yearning to explore not just physical space but the space of the unknown, is perhaps the most distinctly human thing about us. It is what drove us to cross oceans, climb mountains, venture to the poles. It is what sent us to the moon. What pushes us to build ever larger telescopes, send probes to the edge of the solar system, search for planets around other stars. We explore because it is what we do, because the alternative, accepting limits, staying within the known, never asking what lies beyond, feels like a kind of death. S1 might be a planet, or it might be nothing, but the act of searching, of pointing our best instruments at the nearest star and asking, what worlds orbit there? That act is meaningful regardless of what we find, because the search itself is an expression of hope, the belief that knowledge is possible, that the universe, however vast and indifferent, can be understood. Here is the strange truth that Alpha Centauri forces us to confront. The cosmos is not distant. We think of space as something remote, unreachable, the realm of galaxies billions of light years away, events that occurred before. Earth formed, scales so vast they exceed human comprehension. And that is all true. The universe is unimaginably large. Most of it is forever beyond our reach, but sometimes, right now in fact, the cosmos is 4 light years away, close enough to see with the naked eye, close enough that a message sent at the speed of light would arrive before a presidential term ends, close enough that the most advanced probe humanity could currently build might reach it within a century. The line between here and there, between Earth and the cosmos, between the known and the unknown, is not as sharp as we imagine. Alpha Centauri exists in a strange middle space, too far to visit easily, close enough that visiting is not impossible, distant enough to require our best instruments, near enough that those instruments can actually see details, and somewhere in that middle space, in that region between the familiar and the unreachable, we found a signal, a faint point of light that might be a world, or might be a ghost. Either way, it is there. 4 light years from here, next door, in cosmic terms, a reminder that the universe is not something separate from us, something that only exists in distant galaxies or ancient pasts. The universe is here, now, orbiting the star next door, waiting to be understood. We began this journey with light from next door, photons that left Alpha Centauri 4 years ago, that travelled through the void, that entered Webb's mirrors and created patterns in detectors. That became data, analysis, orbital models, predictions. We followed those photons through the complexities of what they might mean, through detection and disappearance, through hypothesis and uncertainty, through the careful, patient process of science trying to distinguish signal from noise, and we have arrived here, at a moment of pause, waiting for more light, more photons, more data that will either confirm the story those August signals told us, or reveal them as illusions. The light will come. August 2026 is not far away. The photons are already travelling, already on their way from Alpha Centauri to Earth, carrying information we cannot yet interpret, information that exists but remains unknown. When those photons arrive, when they strike Webb's detectors, when they are processed and analysed and compared against predictions, we will know more than we know now. Not everything, perhaps not even enough to claim certainty, but more. And that is all science ever promises, not final answers, just better questions, slowly accumulating evidence, the gradual refinement of uncertainty into knowledge. The story of Alpha Centauri is not over. The story of S1 has just begun. We are living in the middle of it, the uncertain part, the waiting part, the part where we do not yet know how it ends. But we will keep watching, keep observing, keep following the light from next door, because that is what we do, because the nearest unknown is still unknown, and because someday, perhaps soon, perhaps not for years, the universe will answer.